Hey class, today we're going to be talking about section 2.5 for college algebra, which is basic transformations of some functions. So before we get into transforming them, I just want to quickly review all the functions that we have covered so far, either in this class or your previous classes, a little bit of detail about each one. So you might want to pause this video right now, go to the calendar and make sure you've got this first page filled in, and then you can just kind of listen to me explain things. So we have constant functions, which is y equals a number. It's when we have a zero slope. It's just a horizontal line. Domain is all real numbers. The range is whatever that y value is. In math, we use little curly brackets for lists of numbers. So you could do little curly brackets with just a 2 in it, or you could say y equals 2 if that's easier for you. There are no increasing or decreasing intervals, and this is an even function. So we covered even and odd functions in a previous lesson, which means it's symmetric to the y-axis. The identity or linear function is the function y equals x. So these are all, with the exception of the constant function, these are all the parent graphs of all these different types of functions, so no transformations. So we have y equals x. Domain and range are all real numbers, increasing intervals. So the y equals x without being transformed is always increasing over its entire domain from negative infinity to infinity. Just a quick reminder, when you do increasing and decreasing intervals, you always use x values. So those are x value intervals. It's never decreasing, and it is an odd function, which means it's symmetric to the origin. The absolute value function looks like a V. I always say absolute value with V's, and it looks like a V. And so we have that absolute value because it always makes anything positive. So if I put a positive x or a negative x in, it's going to make that y value positive. Domain is all real numbers. Range is not. So range goes from 0 to infinity. It includes the value 0 because the absolute value of 0 is 0. So we use a square bracket on 0. It is increasing from 0 to infinity, decreasing from negative infinity to 0. So again, those are x intervals. And we never include the endpoints in increasing, decreasing, or constant intervals. So they'll always use rounded brackets for that. This is an even function because it's symmetric to the y-axis. We've gone over quadratic functions. Y equals x squared is our parent of that. Domain, all real numbers. Your range goes, again, from 0 to infinity, including 0. So we use that square bracket. This is really similar to the absolute value function, actually. Increasing interval from 0 to infinity, decreasing interval from negative infinity to 0. Remember, interval notation, you always do the lowest number and then the highest number. And this is also an even function because it's symmetric to the y-axis. If you are wondering how I got all these graphs and you're not quite comfortable enough to just know which points go where, you can always make tables of values and figure out the points. I'll kind of show you how to do that with the cube root function because that one's probably the one we've seen the least. So square root function has a definite starting point because remember, the square root of anything negative is going to make it an imaginary number, and that's not going to show up on our real graph. So the smallest real number square root is going to be the square root of 0. So we have that starting point at 0, 0. And we can go from there, positive x's. So domain goes from 0 to infinity, including 0. So does the range. We are always increasing over its entire domain, but again, we do not use square brackets for increasing or decreasing intervals. So from 0 to infinity, it doesn't decrease, and it is neither even nor odd. It's not symmetric to the y-axis or the origin. So this one's a neither. Cubic function, so y equals x cubed, looks like that. Domain is all real numbers, so is the range. It's always increasing over its domain from negative infinity to infinity. It is never decreasing, and it is an odd function because it's symmetric to the origin. And then this one, I'm just going to do a quick table of values so you can see where I'm getting these numbers. So we have the cubed root of x. So if x is 0, the cubed root of 0 is 0. If x is 1, the cubed root of 1 is 1. Then what's the next perfect cube? So what's the next cube root that's going to give me something easy to graph? Well, 1 cubed is 1, 2 cubed is 8. So if I do the cubed root of 8, I get 2. And then I can go negative as well. Negative 1. If I have the cubed root of negative 1, I get negative 1. It's not like square root where I get an imaginary number because I can take -1 cubed, and I get a negative number, -1. And then I can do -8. The cubed root of -8 is -2. So that kind of gives you all those points. 8 and 2s wouldn't fit on my graphs. So just be careful not to cross that y = 2 boundary as you go towards the end of your graph there. Domain is all real numbers. Range is all real numbers. Slowly but surely, that range, the y values will go up and down to the infinities. It is always increasing over our domain from -infinity to infinity. It is not decreasing, and it is an odd function because it's symmetric to the origin. That's a lot of information. And at this point, you are expected to know how to graph at least the parent functions of all of these types of equations. So if you're struggling with this, come see me for help, please, if you're one of my students. All right. So the next page, we're going to talk about transformations. So given a parent function f of x, describe the transformation that each part of the function does to f of x. So we have this big formula here, g of x equals a times f of b times x minus c plus d. So this is what we call transformational function form, which is a mouthful, but that's what it's called, transformational function form. It's what it is. It's the equation for g of x in terms of f of x and how f of x was transformed to get g of x. So each piece here, a is our vertical dilation. It can be a stretch if a is greater than 1. It can be a compression if a is between 0 and 1, like a fraction or a decimal between 0 and 1. If a is negative, it reflects our graph over the x-axis, which is a little tricky, actually. It's almost better to think about the reflection as just a vertical reflection, because if you do your shifts, your translations first, and then reflect it, you're not actually reflecting it over the x-axis. You're just going to be reflecting it vertically, which is what I end up doing. B is a horizontal dilation. So the stretch and compression pieces are actually backwards. It's the opposite direction. If B is greater than 1, it's actually a compression horizontally. If B is a fraction between 0 and 1, it's actually a stretch horizontally. So that gets a little confusing. It's a lot safer to just say horizontal dilation of a factor of blank. Then you're right no matter what. If B is negative, it reflects it over the y-axis, or again, that reflection horizontally if you do your translations first. C is a translation right and left in the opposite direction that you think it's going to be. We'll go over an example. And D is a translation up and down. So let's look at some examples. We have this weird, funky graph on the side here. It's got like a thing and then a little V. So definitely this is actually a piecewise function, which I've covered previously. But we don't need to worry about the equation. We're just going to take this function and translate it or transform it. So part A, x minus 1. So remember, x minus c. That's going to be our horizontal translation in the opposite direction. So instead of going left, we're actually going to go right. We're going to go right 1. So it's in the opposite direction that you think. And then we're going to go up 2. So if I take each one of these points and I move them, so let's just start with our, I guess, leftmost point, -4, 0. If I take that 1, 2, 3, 4, -4, 0, and I go right 1 and up 2, it goes to here. Then -2, 4, 1, 2, 3, 4 would go up 2 and over 1. It kind of goes off our graph, but that's all right. 0, 0 would go right 1 up 2. And then in 2, -2, 1, 2, -2 goes, so I'm kind of like putting a point there and then moving it. So right 1 up 2, and then that's kind of what I'm doing in my head here. So I'm taking that point and I'm going right 1 and up 2 and getting my new point. All right, and then the last one, whoops, I can't get that erased. Okay, 4, 0, so 1, 2, 3, 4, 0, right 1 up 2 is there. And if you notice, if I connect these like the original function, it looks exactly like the original function, just the entire thing has been moved right 1 and up 2. The next one, we have a vertical compression of 1/2. So what that does is it it multiply the y values by 1/2. So whatever that a value is, it gets multiplied to the y value. So my x values aren't going to change, which means my x-axis values, the x-intercepts, are not going to change, because if I multiply 0 by anything, it's still 0. So I can actually start by putting all of those on my graph. And then -2, 4, it's still going to have an x value of -2, but the 4 is going to be compressed by 1/2. So it's going to go -2, +2. So it's going to be half as tall. And then same with the bottom point of the V piece is going to be compressed by 1/2. So it's only going to go down to -1. The x value doesn't change. So x's don't change, but the y's are compressed by a function or by a factor of 1/2. Similarly here, I have a couple things, a vertical stretch of 2, and I have a reflection across the, I'm going to say x-axis, but you can also say a vertical reflection or in the vertical direction. So what's going to happen with these is all the y values, so similarly to the other ones, we're going to multiply the y values by -2. And that's going to do everything for us. Any a value, just multiply it to your y values, and you got it. So -40 still is -40. 0, 0 hasn't changed because the y pieces were 0. If I multiply 0 by anything, it doesn't change. Now, -2, 4 is going to become -2, -8. So that 4 gets multiplied by -2. I don't even think this is going to fit, but I'm going to do my best. 1, 2, 3, 4, 5, 6, 7, 8. Sure. This is going to be -2, -8. And then we have 2, -2. Fix that here. Is going to be 2 and then +4. So if I take -2, multiply it by -2, I get 2, 1, 2, 3, 4. All right, so this part of it is still that kind of parabola shape we had. And then this one is still the V shape we had there. All right, now let's talk about the B value. So our horizontal dilations. This one is going to be a horizontal compression. And again, if you just want to say horizontal dilation of 2, that's fine. It's a horizontal compression of, well, gosh, I'm not sure whether or not to say 2 or 1/2. I think I'm going to say 1/2 because that's kind of what's happening is it's compressing it by a factor of 1/2. It's backwards. So what we're going to do when we have a B value is instead of with the A, we multiply Y by A. Here we're going to divide X by whatever the B value is. In this case is 2. So I can take all my X values and divide them by 2. So it's going to take my graph and shrink it horizontally. So -40 and 40 are going to get shrunk down to -20 and 20. 0 isn't going to change. So instead of doing this, it's now here. And then -2, 4 is going to become, so if I multiply -2 by, or sorry, divide -2 by 2, it's going to become -1, 4. So it's still going to go up to 4, but the X value has been divided by 2. Same with 2, -2 is now going to be 1, -2. So I have this pretty skinny little graph now here, like that. All right, and then here we have a reflection over the y-axis. So again, you can just, not multiply. I want you to think B value is always divide X by -1 is another way to do it. So I want you to think divide when we think about the B value. So -40 switches to +40. +40 switches to -40. 0, 0 doesn't move. -2, 4 switches over the y-axis to +2, 1, 2, 3, 4. And then 2, -2 switches over to -2, -2. So be careful when you're drawing this. This is the parabola part. Oops, it's not perfect. That's all right. And then the V part. Right, so that's kind of a basic idea. You're going to be applying these transformation properties to different types of graph. They're not all going to be weird like this. They might just be parabolas or cubic functions or square roots or whatever kind of function you have that's given to you. All right, and that's it for today's lesson.